Roll a ball at a hill taller than it can climb, and it always rolls back. It simply does not have the energy to reach the top. Yet in the quantum world, a particle facing such a wall can sometimes appear on the far side, having crossed a barrier it could never climb. This is quantum tunneling. Picture a particle with energy E, approaching a barrier of height V0, taller than E. In classical physics the rule is absolute. If E is less than V0, the region inside the barrier is forbidden. The particle is turned back, every single time. But a quantum particle is not a point. It is a wave function, governed by the time-independent Schrödinger equation, minus h bar squared over 2m, times the second derivative of psi, plus v psi, equals e psi. Solve it, and the particle's behavior at a barrier becomes far richer than a simple bounce. Even where a region is classically forbidden, the wave function does not stop dead at the wall. It leaks in, decaying exponentially, not oscillating. We see this in a finite well. Its bound states have only certain discrete energies. Inside the well, the wave function oscillates. But at each wall it does not fall to zero. It penetrates into the forbidden region as a decaying exponential tail. And the higher the state, the more nodes it carries. Now make the forbidden region thin, a barrier of finite width. A wave packet, representing the particle's probability, travels in from the left. At the barrier, part of it is reflected back. But part survives, decaying exponentially across the barrier, and emerges on the far side, smaller, but real. The particle has tunneled. And throughout, total probability is conserved. Reflection plus transmission equals 1. How likely is it? For a wide barrier, the transmission probability falls off exponentially. Roughly, e to the power of minus 2 kappa a, where kappa is the square root of 2m times the quantity v0 minus e, all divided by h bar, and a is the barrier width. The lesson is dramatic. Make the barrier just a little wider, or a little taller, and tunneling becomes vanishingly rare. It is fantastically sensitive. And this is no curiosity. It runs the universe. In alpha decay, an alpha particle tunnels out of a nucleus that should trap it. In the scanning tunneling microscope, electrons tunnel across a tiny gap, letting us image single atoms. And in the heart of the sun, protons tunnel through their mutual repulsion to fuse. Without tunneling, the stars would not shine. A particle passing through a wall it cannot climb. Not magic, but the simple consequence of being a wave. In quantum mechanics, forbidden does not mean impossible. It only means unlikely.